Welcome back, students. In this video segment, we will cover section 7.4, integration of rational functions by partial fractions. So we continue on our journey to learning a handful of techniques, of really powerful techniques for evaluating the types of integrals that occur in STEM field mathematics courses, specifically engineering and physics, etc., etc. So let's start out with an example. Let's take a look at our first example. Suppose we want to consider the integral of -2 over x squared minus 1 with respect to x. So you can see from the title, we're integrating rational functions, and this is in fact a rational function. Remember, a rational function is nothing more than the quotient of two polynomials, and polynomials are just sums and differences of powers of x. So this fits the bill. We could actually solve this particular integral by making a substitution from a previous section. Can you see it? Your hint is there's no radical sign in the denominator, but we can still use that method. It would be trig substitution, and the substitution would be, can you remember? Well, it's not x equals sine theta, because it would need to be 1 minus x squared. So it's x equals secant theta. If you were thinking that, that's correct. Okay, now here's how the method goes. Suppose we knew, and this, what I'm going to write is actually true, but suppose we knew ahead of time that the function we were integrating was equal to 1 over x plus 1 minus 1 over x minus 1. Then the problem would be over. Then, that's a big if though, if we knew this. This is what the whole section is really based on, is knowing this or becoming knowledgeable of this sort of breaking down the rational function into simpler rational functions. If we knew that, then the integral would be very, very simple. We would be integrating 1 over x minus 1 minus 1 over x plus 1 minus n over x minus 1. And each of these are very simple integrals. The first would be the natural log of the absolute value of x plus 1 minus the natural log of the absolute value of x minus 1 plus a constant. And we could use the law of logarithms that says the log of a over b equals the log of a minus log of b, to combine this to maybe one expression. Okay. So our task is to take that original -2 over x squared minus 1 and break it down into simpler fractions, fractional expressions, simpler fractional expressions. Okay, those simpler fractional expressions are called partial fractions. So these simpler expressions are called partial fractions. Okay, the idea again, take a complicated, or even not so complicated, but to take a fairly complicated rational expression and break it down into simpler partial fractions that are maybe a little easier to evaluate. Okay, so what we're going to do is we're going to break this down into two major cases. Case 1 and case 2. Case 1 may take us 20 or 30 minutes, or a little more maybe. Case 2 maybe takes us 10 minutes. So case 1 is really the big, this is really where we're going to need to take most of our work. So let's take a look at what do I mean by case 1. So let's consider integrating a rational function, p of x over q of x, where p of x and q of x are polynomial functions. And case 1, the big case for us, is where the degree of the numerator is less than the degree of the denominator. So if the degree on top is less than the degree on the bottom, degree on the numerator is less than the degree on the denominator, we have this major first case. What we're going to do is we're going to break this major first case down into a few subcases. Okay, so let's say we're looking at case 1, comma, Roman numeral 1. Okay, and this case is where the denominator is the product of distinct linear factors. That's a really big chunk to chew. The denominator is the product of distinct linear factors. So what does that mean? What does it mean to have the denominator the product of distinct linear factors? Well, look back at the original example, negative 2 over x squared minus 1. I can rewrite the denominator by factoring x squared minus 1 as the difference of squares into negative 2 over x plus 1 times x minus 1. So the denominator is the product of distinct linear factors. Remember, linear factors are factors that if you would graph them separately, they represent lines. And x plus 1, y equals x plus 1, and y equals x minus 1 are equations of lines. Okay, so this first case says that we can factor the denominator as the product of distinct linear factors. So let's just dig into the method. Here's how it goes. What you do once you've factored the denominator into distinct linear factors. By the way, what does the word distinct mean? The word distinct here means different factors. So we're not looking at x minus 1 times x minus 1 again. So each of the factors is different or distinct, okay? What we do is we sort of go backwards from what we did in algebra. In algebra, this would be the final result, this negative 2 over x plus 1 times x minus 1. We assume then we're going to go backwards and ask ourselves, well, what two fractions could have been added together to get this? And then we would set up those two fractions. How do we get those two fractions? Well, look at the denominator. The denominator is x plus 1 times x minus 1. That's the least common denominator of two fractional expressions, one with x plus 1 and one with x minus 1. So the first thing is we assume we can break down the rational expression into the sum of simpler expressions. And our goal is to figure out what the numerators should be in those simpler expressions. Then we perform some algebra. Once we make this assumption that we can break the rational expression that we're integrating into the sum of simpler expressions, we go after a and b. And what we're going to do is we're going to multiply both sides by the least common denominator of x plus 1 times x minus 1, and ultimately figure out what those constants a and b should be. Okay, so if I multiply both sides of the equation now that I formed with these partial fractions, on the left-hand side, both the factors in the denominator will cancel, and I'm left with distributing that x plus 1 times x minus 1 into the left-hand side. So if I multiply x plus 1 times x minus 1 times a over x plus 1, I get a times x minus 1. The x plus 1 cancels out. If I multiply the second, the x plus 1 times x minus 1 times the second fraction, the x minus 1 cancels, and I'm left with b times x plus 1. Okay. Now, our goal, as it was a few minutes ago, still remains to find the constants a and b that should make this true, that make this equation work out. There are two methods for doing this. There are two methods. Well, I think there are more than two methods for doing this, but there are two popular methods for doing this. I'm going to show you the one that's most common in textbooks first, and then I'm going to show you the second method, which I choose to use myself. I just prefer the second method. So let's dig in. Method, let's say the first method, method 1, and I'm only calling it method 1 to distinguish it, just to distinguish the two methods. I'm not saying method 1 because method 1 is more important. In fact, it's not the one I use myself. You choose what's good for you. The first method, method 1, says multiply everything out on the right hand side. Ax minus a, distributing the a, bx plus b. Factor out, or rather group the powers of x together. So you have ax plus bx, and the constant term minus a plus b. Factor out the x from the first two terms, and maybe group the negative a plus b. And all of this is supposed to equal negative 2. Now this equation is supposed to hold true. We don't solve for x, we're solving for a and b. It's supposed to hold true for all x, no matter what x we put in. I'm going to slip in on the right hand side a 0x. So if I'm going to assume that this equation holds true for all x, then I should be able to equate the coefficients together. So I should be able to state that a plus b then should equal 0. Okay. Well, if a plus b, the coefficient of x, should be 0, what should the constant term be? What should negative a plus b be equal to? Well, let's trace out or follow what the corresponding terms would be on each side. Negative a plus b, the constant on the right, should equal the constant on the left, negative 2. And then solve for a and b. So in this method, we set up a system of equations, and the system of equations will have usually as many equations as there are constants defined in the partial fractions decomposition. I think this is the first time I use the term decomposition to identify the partial fractions. So what we're doing is we're just to define my vocabulary here, we're breaking the rational function down into the sum of simpler partial fractions. That's called a partial fractions decomposition. So if I neglected to say that, then there you go. So this particular system of equations is very easy to solve. You've learned a bunch of techniques for solving systems. You could use Cramer's rule. If you've learned matrices, you could use substitution, elimination, which is sometimes called the addition method. I'm simply going to add the two equations together because I noticed that when I add the equations together in this case, that the a's cancel and I get to solve for b. I get 2b equals negative 2, which gives me b equals negative 1, and then I'll back substitute that negative 1 into the first equation, or the second one. So a plus negative 1 should equal 0, so a should equal 1. So once we've solved for the constants that we're looking for, we go back to our original partial fractions decomposition and write out the function, write out that partial fractions decomposition with the constants that we found. So negative 2 over x plus 1 times x minus 1 then is a over x plus 1 plus b negative 1 over x minus 1. So we've replaced in the original rational function the more complicated rational expression with as the sum of simpler rational expressions, the partial fractions decomposition, which can be integrated very easily, and I did that about 10 minutes ago. So let's take a look at another example. We're still looking at case 1, Roman numeral 1. So I want to do another example with this Roman numeral 1 case where we have the denominator as the product of distinct linear factors. So our next example is to evaluate the integral of 5x minus 7 in the numerator over x minus 1 times x minus 2. Okay, so the denominator is the product of distinct linear factors in the function we're integrating. So what we'll do is we'll do a similar thing that we did in the last example, but we'll use a different method for finding the constants, a and b. I promised you we would do a different way of doing this. And this different way, I've said this a couple times, this alternate way is actually the way I prefer to do things, and it's just personal preference. So whether we use the way we just did or the way coming up, we still break down the original rational expression into the sum of simpler rational expressions with the individual denominators. A constant a over x minus 1 plus a constant b over x minus 2. And just as we did before, we multiply both sides by the least common denominator, minus 2, x minus 1 times x minus 2. And then perform the algebra on each side. On the right-hand side, on the left-hand side, denominators cancel out. That's really nice. That's the whole idea, though. And on the right-hand side, if we distribute that x minus 1 times x minus 2 into the original partial fractions decomposition, we get a times x minus 2, the x minus 1 cancels, and the first distributing to the first term, plus b times what? Times x minus 1. If we were to proceed now with the way that I showed you in the earlier example, we would multiply everything out on the right-hand side, then gather the powers of x together and form a system of equations. I'm not going to do that this time. What I'm going to do is I'm going to let x equal a constant. See, this is supposed to hold true for all x, for all values of x. I'm going to let x equal a constant that will allow me to solve for one of the two variables a and b. Now, what could I let x equal on both sides? I just wrote it. Sorry, I wanted to pose the question and give a pause there. If I let x equal, sorry about that, if I let x equal 1 on both sides, then the term on the right with b will disappear, and we'll be left with an equation that has only the constant a. Okay, didn't mean to jump the gun there. So if I let x equal 1 on both sides, I'm going to get on the left-hand side 5 times 1 minus 7 equals a times 1 minus 2 plus b times 1 minus 1, or plus 0. Okay, on the left-hand side I get negative 2. On the right-hand side I get negative a. That tells me that a is 2. Okay, that's pretty nice. No system of equations involved here. It looks simpler. Well, it's not always that much simpler. It's just a preference. I prefer to do this. In this case, it is going to be simpler than the system of equations. So now, and this time I'll wait. I'll pause a second. What should I let x equal so that the constant a will disappear in the original equation? I can solve for b. Okay, well, if I let x equal 2 on both sides, then I can solve for the constant a. So on the left-hand side, if I let x equal 2, I have 5 times 2 minus 7 equals the term with a disappears. I'm going to get b times 2 minus 1. So 10 minus 7 is 3, and 2 minus 1 is 1, so b is equal to 3. That's pretty nice. Pretty nice. So remember, I'm integrating 5x minus 7 over x minus 1 times x minus 2 with respect to x. And I know the two constants a and b are 2 and 3 respectively. So it's 2 over x minus 1 plus 3 over x minus 2. So this becomes the integral of 2 over x minus 1 plus 3 over x minus 2. And those two integrals are extremely simple. I get 2 times the natural log of x minus 1. If you're not sure about that, stop the video and make a u substitution in the first integral if you need, but convince yourself that these answers are correct. So if I integrate 3 over x minus 2, I have 3 times the natural log of x minus 2 plus a constant, and this is fine. We could use the rules of logarithms to maybe write this as one expression, but no, this is fine. This is just fine. Okay, so now let's take a look at case Roman numeral 1. I'm sorry, case 1, Roman numeral 2. Okay, we're still in the case where the degree of the numerator is less than the degree of the denominator, but now we want to look at a case Roman numeral 2. Case Roman numeral 1 was the denominator is the product of distinct, which means different, linear factors. So let's take a look at case Roman numeral 2. So case Roman numeral 2 within this big case 1 that we're looking at is the denominator is the product of linear factors, just like before. The denominator is the product of linear factors, some of which, though, are repeated. So there's the difference between the two cases. Some of them, or all of them, I guess, all of the linear factors, some of the linear factors are repeated. Okay, so what do I mean by that? What I mean by that is, suppose, let's see. Let's go ahead and look at a specific integral. Why not just dig in here? So suppose we're to evaluate an integral that satisfies what we're looking at in case Roman numeral 2. Suppose we're looking at 3x squared in the numerator minus 7x plus 5 over x minus 1. That's sort of like before. But this time we have x minus 2 squared. So the linear factor x minus 2 is repeated. It's x minus 2 times x minus 2. Okay. And we integrate with respect to x. There's a difference here in how we set up the partial fractions. I'm going to show you a fairly common mistake, and then we'll dig into the correct way to do this. So what we're doing in this partial fractions decomposition business, once again, is we're taking a result of adding fractions together that we might have done in algebra, and we're going backwards. We're trying to figure out what the original question should be. In other words, this final rational function, rational expression that we have here, where did it come from? What individual simpler rational expressions were added together to get this? Well, we assume that we could have had a rational expression a over x minus 1, and we also assumed that we could have some other simpler rational expression with the denominator x minus 2 squared. Now this is a mistake, and as I mentioned, it's a fairly common one. This is a mistake. You see, when we look at the result that we, or the rational function that was supposed to be the end result of adding the simpler fractions together, there could have been another fraction involved in getting that. There could have been another fraction involved in getting that. So what am I talking about? Specifically, what's the least common denominator of 3? Let's change it a little bit. What's the least common denominator of 1/2 and 1/3? It would be 6. 6 is the smallest. 6 is the smallest number that both 2 and 3 will divide into. It's a fancy way of saying that the least common denominator is 6. What's the least common denominator now? It's still 6. It's still 6. I'm not sure if I like my example. What's the least common denominator of 1/2 and 1/3 being added together? 6. Let's do it this way. I have a better idea. 9. It would be 18. It would be 18. So what's the least common denominator now? It's still 18. It's still 18. 9 is 3 squared. So our original fraction, 1/2 plus 1 over 3 squared plus 1 over 3, has a least common denominator of 18. Now, if I had just looked at the first two fractions, the least common denominator would be 18. If I add the extra 1/3, the least common denominator is still 18. My point is, when you're adding the fractions together, the least common denominator has to include that highest power that you get in factoring the denominator completely, but it has to include every power below that in the factorization of the denominator. You see that the least common denominator is 2 times 3 squared. So we have to assume that our partial fractions decomposition had 2 in the denominator, 3 in the denominator, and also 3 squared in the denominator. This example was one I did on the fly here. If it didn't make sense, there's a bottom line here. So don't panic if this didn't make sense. The correct thing to do here is this. So let's take a look at the correct thing to do in this problem. In this particular problem, we have 3x squared minus 7x plus 5 over x minus 1 times x minus 2 squared. And what we do is we assume that the partial fractions decomposition comes from a fraction with x minus 1 in the denominator, and every power leading up to the highest power of x minus 2. So b, if that didn't make sense, b over x minus 2 plus c over x minus 2 squared. Okay, and then we hunt for the constants a, b, and c. Okay, now I'll summarize this result when we found the constants a, b, and c. So if this still isn't clear, just bear with me. So let's hunt for the constants a, b, and c. Let's do that right now. So what I'm going to do is exactly what I did in the last two examples. I'm going to multiply both sides by the least common denominator of x minus 1 times x minus 2 squared, x minus 1 times x minus 2 squared on both sides. Then I'm going to continue with the algebra. I'm going to get 3x squared minus 7x plus 5 on the left-hand side. And I'm going to distribute the x minus 1 times x minus 2 squared into the three terms with a, b, and c as numerators. When I do that, I get, in the first term, a times x minus 2 squared plus b times x minus 1 times x minus 2 plus c times x minus 1. Okay? So hopefully I can let x go through different constants and pick off the numbers a, b, and c. Okay, so let's try it. I'm going to use the second method that I described for finding those constants for the rest of this video segment. So I'm going to let x equal, what should I let x equal to get one of those constants? Well, let's suppose we let x equal 2. If we let x equal 2, the terms with a and b will both disappear. So let's let x equal 2 on both sides, of course. Okay, so I'm going to get on the left-hand side 3 times 2 squared minus 7 times 2 plus 5. And on the right-hand side, the first term with a disappears, the second term with b disappears, and I get the third term c times 2 minus 1. I'm going to compute the constant on the left-hand side. 2 squared is 4, times 3 is 12, 7 times 2 is 14, plus 5, and that's c. So 12 take away 14 is negative 2. Negative 2 plus 5 is 3. So c needs to equal 3. Okay. So now what should I let x equal to get another constant? It's pretty clear. I think it's pretty clear. Can you think of it? What should I let x equal? Of course, I should let x equal 1. If I let x equal 1, the last two terms on the right will disappear, and I can solve for a. If you're thinking there's a potential problem here, you're right. If you don't see it, that's fine too. Let's hold on. So let's let x equal 1. On the left-hand side, I get 3 times 1 squared minus 7 times 1 plus 5. On the right-hand side, I get a times 1 minus 2 squared. A times 1 minus 2 is negative 1 squared. So I get on the left-hand side again, 1 squared is 1, times 3 is 3, 7 times 1 is 7, plus 5, 3 take away 7 is negative 4, plus 5 is 1. So a has to equal 1. Now go back to our equation here. Back to our equation with the three constants I need to find. I found a and c. C, a. Done. I found a. I found c. I need b. So here's the question of the ages. What can I let x equal now that will eliminate a and c from the equation and allow us to solve for b? And the answer is, it's impossible to do that. But don't fret. So this problem is a little more difficult using this method than before, but it's not that big of a deal. What we do is we substitute what we found back into the equation. We know a is 1 and c is 3, so substitute that back into the equation that we're looking at, that we're concentrating on now. So I'm going to get 3x squared minus 7x plus 5 equals a 1 times x minus 2 squared plus b times x minus 1 times x minus 2 plus c, which is 3 times x minus 1. Okay, so now we can isolate b. We can solve for b. How? You can let x equal anything you like except for 1 and 2. Okay, look what happens if you let x equal 1 or 2. That the term with b will disappear. We won't get anywhere. You can let x equal the square root of 17 over pi cubed if you want on both sides. I wouldn't do that, but you could. And in fact, what I would do is choose to be gentle on myself. So be gentle on yourself. What could you let x equal that we haven't already let x equal to solve for b? Well, we can't use 1 and 2, but we certainly can use what? And I think I wrote let x equal 2. I have no idea why I wrote let x equal 2. All right, so what should we let x equal? 0 would be just fine. Okay, again, you could let x equal 17 over pi cubed or pi cubed over 17 or anything you like, but be gentle on yourself. So if I let x equal 0, on the left-hand side I get 5 equals, then on the right-hand side I get negative 2 squared. Letting x equal 2, I'm sorry, 0. I keep wanting to let x equal 2 for some reason. So I get b times negative 1 times negative 2. And again, I'm letting x equal 0, so plus 3 times negative 1, and I can solve for b. Okay. I really prefer this method. I know I'm trying to sell it to you, but I do so much better with this method than solving systems of equations. I tend to make a lot of mistakes, little mistakes solving systems of equations. And I've been doing this for a whole lot of years. And I still make a bunch of mistakes doing systems. So combining like terms. So let's solve for b. So we get 2b equals 4 if I subtract 1 from both sides. So b should equal 2. And I've got my 3 constants now. A equals 1, c equals 3, b equals 2. A equals 1, b equals 2, c equals 3. 1, 2, 3. I wasn't feeling very original on this problem. So let's go back to our problem. Our original problem is to integrate 3x squared minus 7x plus 5 over what was it, x minus 1 times x minus 2 squared. And what we did is we assumed that we had the partial fractions decomposition a over x minus 1 plus b over x minus 2 plus c over x minus 2 squared. So we have a over x minus 1 plus b 2 over x minus 2 plus c, which is 3 over x minus 2 squared. Integrating with respect to x, and each of these integrals is very, very simple. Okay. So we have a natural logarithm, another natural logarithm. What's the integral of the last term there? Well, the integral of the last term is not difficult. The last term, you could think about it as 3 times x minus 2 to the negative 1, and if you need to make a u substitution now, you could let u equal x minus 2. So, oh, sorry, it would not be to the negative 1, it would be to the negative 2. So we add 1 to the exponent. If we add 1 to the exponent, we get negative 1 as the exponent. Divide by that new exponent. That's where we get the negative. So we get negative 3 over x minus 1. Stop the video and confirm it if you're not okay with that. Plus a constant. Okay, so this is an example of case 1, the big case 1, Roman numeral 2, where some of those linear factors could be repeated. So I'm not gonna actually integrate this one, but suppose we had something like I like 17 a lot for some reason today. 17x minus 1 over, let's say, x minus 1 squared times x minus 2 cubed. And we were interested in a partial fractions decomposition. What would it look like? It would look like a over x minus 1 plus b over x minus 1 squared. So we include in the partial fractions decomposition that the highest power that's in that factored denominator, but we also include all the powers below it, down to the first power. So how many more terms are we going to have in this partial fractions decomposition? 3. We're going to have one with x minus 2, another with x minus 2 squared, and a last with x minus 2 cubed. So C, D, and E for our constants. We're not going to look for the constants. This was just to summarize the setup. We would end up with, if you use the first method, a system of 5 equations and 5 unknowns. Or we'd let x go through 5 different values to produce the constants a, b, c, d, and e if you were using the second method. Okay, so let's now take a look at case 1, Roman numeral 3. Case 1, Roman numeral 3. And that case is the denominator now contains what are called irreducible quadratic factors. Irreducible quadratic factors. So what is a quadratic factor? Well, a linear factor has the first power in it. It's the highest power. A quadratic factor then has a quadratic factor, which means the highest power is 2. And we don't have repeated quadratic factors. Oh, irreducible. Irreducible means we can't factor it over just whole numbers. So x squared plus 5 is irreducible, but x squared minus 4 is reducible. We could factor it into x minus 2 times x plus 2. So the x squared plus 5 would be irreducible. And x squared minus 4 is not irreducible. It's like a double negative. Not irreducible means it's reducible. We could factor. Okay, so let's take a look at a specific example. Specific example is to evaluate, and the integral looks like 3x squared minus 3x minus 1 all over, let's see, x minus 2 times x squared plus 1 with respect to x. In this case, we have a linear factor, x minus 2, and an irreducible, can't be factored using whole numbers, x squared plus 1. Okay. So let's dig in. What does the method say? The method says this. The method says essentially the same thing for all these cases. We have the result, the algebraic result of adding simpler fractions together, and we want to go backwards and produce what the original fractions were. We assume that the x minus 2 in the denominator correspond to a fractional expression a over x minus 2. Now here's the difference. From the last cases, we do assume that we have a second fractional expression with x squared minus 1 in the denominator, but we don't assume that the numerator is a constant b. We assume the numerator is of degree exactly 1 less than the denominator. The degree of the denominator is 2, so the numerator will have a polynomial of degree 1, bx plus c. And that's the key. When you have irreducible quadratic factors, you assume the numerators have a constant x plus another constant, bx plus c in this case. Okay, let's find the constants a, b, and c using the same procedure as before. Okay, so I'm going to multiply both sides by the least common denominator of x minus 2 times x squared plus 1. And if you're getting fatigued with looking at all the steps, you can inch forward on the video, speed forward on the video until we get that one-line equation to solve for the constants a, b, and c. But I'm going to show all the steps here. Okay, so we're going to hunt for the constants a, b, and c. On the left-hand side, I'm going to cancel all the denominators, all the factors in the denominator. On the right-hand side, I'm going to distribute. So left-hand side gives us 3x squared minus 3x minus 1. The right-hand side gives us a times x squared plus 1 plus bx plus c times x squared plus 1. Oops, nope. Bx plus c times x minus 2. Okay. Just as before, you could multiply the constant and multiply everything out on the right, gather the powers of x together, set up a system of 3 equations and 3 unknowns. I don't like that method for myself. I'm going to let x go through different values to pick off the constants a, b, and c. So how could I get rid of everything except for a? I could let x equal 2 on both sides. So if I let x equal 2 on the left-hand side, I'm going to get 3 times 2 squared minus 3 times 2 minus 1. On the right-hand side, I'm going to get 2 squared 4 plus 1. Back to the left-hand side, 2 squared is 4, 4 times 3 is 12, 3 times 2 is 6, minus 1. And all that should equal 5a. 12 take away 6 is 6, 6 take away 1 is 5, equals 5a. So a equals 1, real simple constant. Of course, I make things real simple in lecture. Okay, so let's hunt for the constants b and c now. Well, it's going to be difficult to find a real number to substitute in for x to make a disappear. In fact, I'll be a little more firm about that. The coefficient of a is x squared plus 1, or a is a coefficient of x squared plus 1. And x squared plus 1 is always positive. In fact, it's always at least 1. So it's not going to disappear with real numbers for x. So what I'm going to do is I'm going to substitute a back in to the both sides of that original equation. A is 1, so that leaves me with 1 times x squared plus 1 plus bx plus c times x minus 2. Now, what could I let x equal to get rid of one of those two constants b and c? And I'm going to draw an arrow for a hint. I want to let x equal something that will make that term go away. It would make the beat go away. Let x equal 0, of course. So let's let x equal 0 on both sides. If I let x equal 0 on the left-hand side, I get negative 1. On the right-hand side, I get 1. plus c times x equals 0, 0 minus 2, so c times negative 2. So I get negative 1 equals 1 minus 2c. Subtract 1 from both sides. So negative 2 equals negative 2c. So c should equal 1. So now I've got a is 1, c is 1. I need b. So what I'm going to do is I'm going to put the constant c back into the equation. So I get 3x squared minus 3x minus 1 equals 1 times x squared plus 1 plus bx plus, we found c was 1, so bx plus 1 times x minus 2. Help me out on this. What should I let x equal to solve for b? Square root of 56? That would work. Not being serious. How about 0.79? That would work. What would be a better choice for x? How about 1? If I let x equal 1, that will allow me to have a coefficient of b of 1, and I can solve for b right off. So let x equal 1. So I have 3 on both sides. 3 times 1 squared minus 3 times 1 minus 1 on the left. Okay. On the right, I have 1 squared plus 1 is 2. Oops. 1 squared plus 1 is 2. Plus, I'm letting x equal 1. So b times 1 plus 1. Letting x equal 1. 1 take away 2 is negative 1. So on the left-hand side, back on the other side, I have negative 1 equals 2 minus b minus 1 if I distribute that negative 1 through. So I have negative 1, combine like terms on the right, equals 1 minus b. So I'm going to get b to the left, so I get positive b on the left, and so add 1 to both sides, b equals 2. And I have my 3 constants. A equals 1, c equals 1, and b equals 2. Let's go back to our original integral and get those constants in there. So our original integral was the integral of 3x squared minus 3x minus 1 over x minus 2 times x squared plus 1. And remember, I was assuming that it came from the fraction, or the rational expression came from a over x minus 2 plus bx plus c over x squared minus 1, or x squared plus 1, sorry. So let's get those constants in. A was 1, b is 2, c is 1, and hopefully this integral that results is easier for us to evaluate than the original integral. Well, the first one is easy. The first integral, 1 over x minus 2, is equal to the natural log of the absolute value of x minus 2. How about that second integral? Well, we can't let x equal, or u equal x squared plus 1. We can't do u substitution because the du is 2x dx. We have that extra 1. So what could we do? Well, here's what we can do. If you want to think about what we should do, you stop the video. Otherwise, I'm going to go forward. I could split this into 2 different fractional expressions. 2x plus 1 and 1 over x squared plus 1. Then it's very, very, very simple to integrate. From the first term, I'm going to get the natural log of the absolute value of x minus 2. The second one, I'm going to get, see if you can guess this now without actually having to go through the u substitution. What is this going to be? The natural log of what? X squared plus 1. Absolute values? No, x squared plus 1 is positive. What about that last integral? This one should be on the tip of your tongue. The very tip of your tongue should be the inverse tangent of x plus a constant. Okay, and that covers pretty much of the big case 1. Case 2 isn't going to take very long. To finish case 1, though, let's just look at one partial fractions decomposition without actually integrating it. For some reason, I'm in love with 17 tonight. So 17x plus minus 1, x plus 1, x plus 2 squared, x squared plus 2x plus 5. Okay, what would the partial fractions decomposition be? A over x plus 1, distinct linear factor, repeated linear factor, b over x plus 2, c over x plus 2 squared, and irresistible, I can't believe I said that. Maybe I'll ask you to identify where I said irresistible on your next test. No, I won't do that. So, it's tempting though. Irreducible, not irresistible. Quadratic factor, x squared plus 2x plus 5. And what goes in the numerator? The degree 1 less than 2 would give us dx plus e. Okay, so that takes care of case 1. Now let's take a look at case 2. It won't take us very long. So in this last case, we're still integrating this rational expression, p of x over q of x, but the degree on the top, the degree of the numerator, is greater than or equal to the degree of the denominator, greater than or equal to it. Okay, so all we'll really require here is one good example. So I'm going to dig into the example and show you how to do this. So example, evaluate the integral of 2x cubed minus 6x squared plus 9x minus 7 all over x cubed minus, oops, not x cubed. Let's see, x squared minus 3x plus 2 with respect to x. So in this case, the degree of the numerator is 3, and that's greater than the degree of the denominator. So if the degree on top is equal to or more than the degree of the denominator, we do this new or this additional case. This is the last case. And it's very simple to describe how to do this. In order to integrate where degree on top is greater than or equal to degree on the bottom, degree on the numerator is greater than degree on the denominator, we use long division first. Okay, so what I'm going to do is I'm going to use long division to divide 3x squared, no, not 3x squared, x squared minus 3x plus 2 into the numerator, 2x cubed minus 6x squared plus 9x minus 7. And this may take some recollection on your part. You probably haven't done a lot of long division since pre-calc. Okay, so I'm going to review that with you here. So the first thing we do is we try to divide x squared into 2x cubed. X squared times what is 2x cubed? Well, x squared times 2x is in fact 2x cubed. So that's the first step. The next step is to take that 2x that I put on the top bar there and multiply it by the remaining factors of terms in the denominator. So x squared times 2x is 2x cubed. So negative 3 times 2x is minus 6x squared. 2 times 2x is 4x. And I subtract, or you can think about it as change the signs and add. I subtract, so I change this to the plus 2 to minus 2, minus to plus, plus to minus, and then add. What I'm going to get is 5x. Then we bring down our next term, 5x minus 7. And we continue the long division if possible. Well, the degree of 5x minus 7 is 1, and we're dividing x squared minus 3x plus 2 into that. So we're done with the division. We can't divide a higher power into a lower power. So that remainder is 5x minus 7. So what that tells us is that our original integral of 2x cubed minus 6x squared plus 9x minus 7 all over x squared minus 3x plus 2 is the same thing as integrating 2x plus the remainder 5x minus 7 over the x squared minus 3x plus 2. Now, that second integral of 5x minus 7 over x squared minus 3x plus 2 should look familiar. That second integral is one that we worked out earlier. It's 5x minus 7 over x minus 1 times x minus 2. We did the work on this earlier. We have distinct linear factors, so what we got earlier was, let's see, I don't remember. Oh, the constants were 2 and 3, so 2 over x minus 1 plus 3 over x minus 2. That saves us a good 5-10 minutes. Wish you could do that on homework, huh? And we integrate. Integral of 2x is x squared. Antiderivative of 2 over x minus 1 is 2 times the natural log of x minus 1. Last integral, 3 times the natural log. The last term, 3 times the natural log of x minus 2, absolute value plus a constant. So the key to case 2 is when the degree on top is equal to or more than the degree on the bottom, the denominator, you use long division first. The long division will then produce some polynomial, in this case 2x, plus a rational expression that is back into case 1. The rational expression that will be left would be the case 1. The degree in the numerator is less than the degree of the denominator. And that finishes this video segment that completes section 7.4, integration of rational functions by partial fractions. Go ahead and dig into homework whenever you get a chance, as soon as you get a chance, and I'm looking forward to talking with you all again soon.